Hello. What's up? Everyone having a good day? Like your hoodie. Thanks. Sponsored by Adidas today. Everyone make sure to go out and get your Adidas gear. Use my promo code. All right. And you can get 93% off all your gear at adidas.com. Hey. All right. This is nice. Getting some hellos from people. Okay. We're really building the community here. Hi. All right. See, I'm loving it. I'm loving the hellos and highs. Even though I don't know who some of you are, but regardless. And this is, I think we've also set a new record now. This will be, what, 6 messages here? 4 different people have put a message in the chat, and none of them have been Austin. Wow, like this is amazing. Hola. I don't really know what that means, but sure, yeah, something. What's poppin', man? See, look how much fun this is. Robin. You know, that's what I would have guessed just based on the fact, not from the initial hello, Mr. Abundance, but from the I like your hoodie. Because Robin, you're typically the one that compliments me on my wardrobe and really boosts my self-confidence every day. So I was thinking that maybe it was you, but couldn't be sure. Yeah, Austin, what's the deal, man? Were you late? How are you gonna let all these people message before you? That's embarrassing, dude. Austin, you clearly don't do math better. Next thing you know, Lewis is going to be putting messages before you. What are you going to do then, huh? You're on time. Did you survive Dairy Queen? Any symptoms setting in? I guess so. It's going bad. If Lewis messages before me, I will join his team. Yes, I joined. Is Lewis in here right now? Lewis, you hearing this, man? I'm looking at the list. I don't think he's in here. Dang. Well, someone let him know that he can get a top tier rugby player on his team. All he has to do is show up and message something before Austin. Man, it's a bold statement, Austin. I hope you're ready to follow through with that if necessary. We got a long several days left. How many followers do I have now? I have 55. No, 54. Up there. As of today, I've now completed all my achievements needed. I could technically have people subscribe to me. Yeah, 54,000. I know, it's pretty crazy. Okay, let's go ahead and start this off. Talking about our growth and decay stuff, like we started yesterday. So, for example, a population of bacteria grows at a rate of 3.7% per minute. There are 12.5 million initially. How long will it take for the population to reach 100 million? So, a brief reminder. That this is our formula for continuous growth or continuous decay, whichever. To identify our key pieces. So just going through at the start, it's growing at a rate of 3.7% per minute. So my rate, or not R, why do I keep using R? K. K is 0.037, and it's positive because it's growing. Now, if this were a problem talking about decaying, then I would have made that a negative, but it's growing, so I want that to be positive. All right, the initial amount, A0, 12.5. So just from there, well, I guess I could also, the question is, how long will it take to reach 100 million? So my goal is to figure out how much time will it take to hit 100. First, let me write my just model. So A of t equals the initial amount, 12.5, times e to the power of k, 0.037, times t. And I want to know how much time. So that makes sense that I don't know what t should be. I'm going to end up solving for t. So I'm going to take my formula that I just made, 12.5 e, 0.037, and I'm going to set this equation equal to 100. Right? That way I can see what number is it that I need to plug in that it will give me 100 as my answer. And we'll solve. Divide by 12.5. Take the natural log of both sides. So when I take natural log of both sides, it'll get rid of e. And then natural log. And then lastly, just divide by 0.037. So I get this expression. And I'll bring up my calculator now. So I'm going to type all this in one go. I'm going to use alpha y equals to create the fraction. Natural log, another fraction, so another alpha y equals 100 divided by 12.5, close parentheses, divided by 0.037. Enter 56. 56.201. All right, again, we're going to go to 3 decimal places, just kind of as our standard. So what is my units? Minutes. To reach 100 million bacteria. And so I'm sure that's the same answer you got whenever you did this warm-up earlier, since I sent you this file at the beginning of the day. So I know you all opened it up and read through it, did some nice, at least on the warm-up, and then we can check it with what I do. It's like the growth of filth in the boys' bathroom. True, which is compounded by the fact that all the handles for the faucets are stolen. So not only is there so much bacteria, but you also can't wash your hands because you can't turn the knob. So tough times. Have you guys been stealing the handles off of your own faucets in your own bathrooms at home too, since you can't do it at school? Or, you walk into the bathroom at your house and instead of just opening it, you kick down the door. Very smart. Very smart. Okay. I mean, yeah, should do it at school. Might as well do it at home too. Right? It's important to keep those, tendencies, those patterns, keep it consistent. Don't want to change your whole routine just because you're at home suddenly. Okay, is that a good thing? All right, so we're just going to continue on with our growth and decay notes today. We're going to just get into a little more in-depth problems. So instead of just solving for t or just doing a simple calculation, we're going to have these multi-level problems that we do. Yay, I'm excited too. I'm super excited. All right, let me move this out of the way for now. And we will journey onward. So some more complicated word problems. On the planet Matopia, we have a radioactive isotope, nadium-55, which is super neat, and it decays at a rate proportional to its amount. That just is telling us that we're going to use our exponential decay formula. Initially, there was 477 grams. After 15.4 thousand years, there is now 340 grams left. What is the rate of decay for nadium-55? Okay. So a lot of information here. Just do some little underlining. Initially, 477. So I will use that as my starting amount. Okay. And we're going to be talking a lot about different timelines and stuff here. I would say it's a good idea to be consistent. We can do things different ways, but I would say probably just make sure you make your initial amount, that A0, just the earliest possible amount that you know. Yeah, I think that's a decent way to go about it. I don't know, but some other people would also like to think, I don't know. I've seen some people choose to do A0 is 340 instead, because that's how much there is now. So some people like thinking about A0 as being how much there is right now. And then some people like thinking of A0 as whatever the first possible amount is. And the answer is you can do it either way. It'll slightly change your equations and your answers based on how you do it, but I don't know. Well, let me get some feedback from you guys here. Which one makes more sense to you? Thinking about A0 as the amount that we know from the earliest amount of time towards the very beginning, or do you like thinking about it as the time of how much we know that there is right now, today, currently, like the current amount? Earliest amount known, earlier. Okay. Sounds good. I will take it that Robin and Aiden speak for the entire class then. So you've been elected the spokespeople. All right, so let's do that. Let's just say we'll make a decision that we'll keep it that it's the earliest decision or the earliest amount possible that we know. So that's fine. We know after 15.4 thousand years, there's 340 left. So I know that in my equation, my formula, whatever it is, if I were to plug in 15.4, I would get 340. They are our representatives, exactly. We live in a representative democracy. So congratulations to them for winning that. Part A, what is the rate of decay? This is a problem that we did, or a type of problem. We did this last time, right? Finding rate of decay. So let me first just make my formula that I know so far. Initial amount 477. E, I don't know what K is. And I don't know how much time just now because T is just the variable in the equation. Okay. The question asks me for rate of decay. So I know that whatever I'm doing in this problem A, I should be looking for solving K. Right. So I'll use my second piece of information that I wrote up at the top here, that if I plug in 15.4, I'll get 340 is my answer. So I'll do 477 e to the k times 15.4, because that's what I'm thinking about plugging in here for t. I know if I do that, the answer will be 340 because that's what the information at the beginning of the problem told me. Right? There's now 340 grams left, 15.4 thousand years later. So we'll solve this line. Okay. I'll go ahead and reorder this 15.4K. 340 over 477. Natural log of both sides. So the natural log gets rid of the e. Divide both sides by 15.4. So I end up with this expression. I'll do my calculations. Alpha y, oh, turn it on. Make sure to turn your calculators on before you use them. That's a critical step. A lot of people forget that. Alpha y equals natural log. Alpha y equals again 340 divided by 477, close parentheses, 15.4, negative 0.019. So since I'm rounding to 3 decimal places instead of 19, that'll round me up to 0.022. It makes sense that I get a negative answer here because we're solving for K. We're solving for the rate. Well, in this problem, it is a decay problem. So it 100% makes sense that when I solve for that rate of decay, it should be negative. It has to be negative if we're talking about things decaying. So what this means, so this decays at a rate of 2.2% per 1,000 years, I think. Yes, 1,000 years. Do you like how even my brackets are and how they're definitely the same size? Okay, so again, let me ask you a question here that I'd like some feedback on, not necessarily from just two people, but anybody who has a genuine opinion on this. Would you be okay with, so like I said, on kind of bypassing some of these solving steps, if when we're in this line right here, and we're doing our same steps over and over again, divide 477, natural log both sides, divide 15.4, would you be okay with me going straight from that line to here? You know, if I did not write out this stuff, would you still understand and know how I got there? Yes, sure. Yes, go ahead. That makes sense. Since I have my master's degree, you probably should refer to me as master. Yeah. Also like a Jedi master. It's kind of fun. Okay, cool. So yeah, I'll do that in the future. I'll just be going on from that line to that next one. And if you're confused, then just say something and I'll do the steps if we need be. But like, those steps are so repetitive every time that I don't know that we need to write it all out. But if you want to, or if you want to make sure that you're not screwing anything up, you know, to double check yourself, then great, do it. That's fine. Right. So I have my rate of decay. Question's not done though, because part B asks how much would be left after 20,000 years. Okay, from the beginning. So this makes sense. Our equation is good because we decided to use initial amount as the very beginning of whenever we started having this stuff. So let me now write out the formula that I have. A of t equals 477 E. We didn't know what K was before, but now we do. Negative 0.022 times T. All right, so now we have a fully realized formula since we figured out K. So how much would be left after 20,000 years? Well, great. Since we have a formula, let's just make T 20, and we'll just plug in 20, see what we get. 477 E negative 0.022 times 20. And we'll calculate. 477. Remember, E is usually just behind the ln, so second ln, negative. Make sure you use the negative button, not the minus sign. 0.022 times 20. 307.2053, so 0.205. And we're talking about grams after 20,000 years. Right, of Nedium 55. And again, like I mentioned yesterday, using this radioactive decay for various elements now, obviously Nedium 55 isn't a real element for planet Earth. It's only on the planet Mathtopia. But we do use our elements on Earth here to determine how old things are, like artifacts or bones or, you know, mummies and different, anything that we kind of find buried. We can use different radioactive isotopes and measure them and calculate how old something was or when it was alive. It's kind of neat. So in future problems, though, so I broke this down into a part A, part B. Part A, what's the rate? Part B, how much would be left after 20,000 years? In the future, when we do problems like these, it will not have part A, part B. It will probably just say this. The question will just be, how much would be left after 20,000 years? In order to figure that out, we still have to find the rate of decay, that part A, but we'll have to just know that, oh, if I want to figure out this, I need to first figure out the rate of decay. Okay, so you'll have to do various steps of solving in these further problems where, you know, it won't explicitly be listed out into individual, part A do this, part B do this, part C do this. We'll just have to be able to look at the problem and realize, oh, if I want to solve for this thing, I'll need to first find the rate of decay. All right, so kind of some intuition involved here in what we know and what we need to find in order to actually figure out the final answer. So it will be common that we first need to figure out what's the rate of decay. Next up, 720 grams of nerdium-13. Not sure what planet this is on. 9.4 million years ago, and currently there are 400. How long will it take from today to decay to 275 grams? Okay. So again, like we talked about, let's go ahead and just decide to use the earliest amount as the initial amount, the A0. So 9.4 million years ago, there was 720 grams. So 720 grams initially. That's the earliest information that I know of how much of this stuff that there was. Currently, 400. So whatever my formula ends up being, I know that if I plug in 9.4, I should get 400. 9.4 million years go by. Now I'm left with 400 grams. Question. So again, my goal is to figure out how much time will it take to reach 275. So here's the formula as I have it now. A of t equals 720 e to the power of k times t. So this is just like what I said. This problem does not say anywhere, hey, find k. Figure out the rate of decay. It doesn't tell me that, but I'm looking at this and realizing if I want to know what or how much time it will take to get to 275 grams, I will need to know what K is. So my first kind of intermediate goal is before I do my final answer, I first need to figure out what in the world is the rate of decay. So let's do that. So 720 e to the power of k. And now I'm going to use this initial information that I had over here. I know that if I plug in 9.4, the answer that I'll get is 400. And we solve. So I'm going to do my quick solve. K equals. So on both sides, I would divide 720. Natural log. It's a straight line, not really a parentheses. Divide by 9.4. And we're calculating. Natural log 400 720 divided by 9.4. K equals negative 0.063. Right? And it'll be important, this rounding, I mean, I know the difference between 0.62 and 0.63 doesn't seem very significant, but it is important. It will, depending on the problem, it could drastically change our answer, like our final answer. And especially whenever you guys end up doing this on a PFA, or if you've already done it on a PFA, I made all those problems from the PFA. And whenever I calculated the answers, when I put the answers in, I used rounding 3 decimal places in order to do it. So if you're doing a PFA and you get a different answer and you're like, but it's like maybe kind of close, but you're not sure, well, did you round correctly? Because I did all those PFA questions assuming that I rounded to 3 decimal places whenever I needed to round. Are you enjoying this, Mr. Abundance? Of course. What's not to enjoy? I'm still doing math, so I'm having a great time. Are you guys enjoying this? You must be, because that's, you're here. I don't see why anybody wouldn't be enjoying it. You get to listen to me sit here and talk to myself, which is what I do for, 4 hours a day now. I just sit here in this empty place and talk to myself. Tough times. But I'm enjoying it. It's good. Okay. So I found the rate of decay. It makes sense that it's negative. It should be negative since it is decaying. Now I can actually figure out how long will it take to get to 275. So let me write what my formula should be now. A of t equals 470, right? Not 470, 720. Where did I get 470 from? 720 e negative 0.063 times t. Same formula that I had from before, except I now know what k should be. Okay. So now, how long will it take to reach 275? So I'm trying to figure out a time. So 720 e to the negative 0.063 t. If I set that equal to 275, I can now solve for t. I can solve for how much time will it take to reach 275. So same thing. I'm going to quick solve this. 275 divided by 720, natural log of both sides, divided by negative 0.063. Get my calculator out of the way. Natural log. When you do your decay, make sure you're clicking this negative button at the bottom, okay, and not the minus sign from the right side. Negative 0.063. $15.277 thousand years. Is that what the units are? Oh, million years. Sorry. 15.278. No. Because if I'm looking at 27746, so if I'm trying to round to 3 decimal places, then I only look at this immediate next value. Right? You guys can't see that arrow. I only look at this immediate next value, which is the 4. So I understand if we rounded the 6, that would move the 4 up to a 5, which would then move the 7 up to an 8. But since I said 3 decimal places, then we only need to look at the 4th decimal place. Even if there's bigger numbers after that, we're just looking at the 4th decimal place so that we can round to the 3rd. All right, so this would stay 277. Does that make sense? Now, this is not our final answer because, so let's think about what happened, what all happened. There was 720 grams initially, and then after 9.4 million years, we are now, today, there is 400 grams. Okay. And what we just calculated is it takes 15.277 million years to get to 275. But remember, we chose the initial amount to be 720. So what this formula calculated was from when there was 720 until there's 275, how much time is there between that? Okay, so actually, we just found that from the very beginning up until, not now, but in the future, 275 grams, $15.277 million years. And what the question actually asked was, how much time is there from today? Right? Remember that. Or how long will it take from today? So 15.277 is the answer if the question had asked from the very beginning, right? Compared to 9.4 million years ago, how long will it take? Well, then yeah, 15.277 million years. But this didn't ask that. This asks from today, currently. So what we actually want to find is how much time was this piece right here. Right? But hopefully from this visual, it's easier to see that, okay, so all we have to do in order to figure that out is just subtract, right? We know that first chunk is 9.4 million. We know the full length is 15.277. So to find this other chunk of it, we'll just do subtraction. So 15.277 million years minus 9.4 million years. I'm already sick of writing million years, so I'm going to write MY, the standard abbreviation for million years that everybody uses, of course. And I would get 5.877 million years to reach 275 grams. And remember, that's from today. Right. If the question had asked from the very beginning how much time, then 15.277, but it didn't ask that. Okay, so as these problems get harder, we kind of have to do a lot of thinking about making sure our timelines are set up well, and that we understand from what are we, where and when are we talking about and how much stuff was there. So we might have to take our final answer and maybe do just like a tiny bit of adding or subtracting with it to figure out the actual piece. Okay. That was definitely more confusing. So please hit me with some questions. Guess not. I just explained it so well that no questions. Yeah, makes sense. Okay. All right, well then let's try our last one. All right. For some reason, I have 600 grams of a radioactive isotope, uranium-235. In 8.2 hundred million years, it would decay to 268 grams. How much uranium-235 was there 13.5 hundred million years ago? Let's start by writing out our information. So A0, the initial amount. Now we decided we're going to make that just the earliest amount that we actually know. So the earliest amount we actually know how much there was is that currently I have 600 grams. I know I'm trying to figure out 13.5 hundred million years ago, but I don't know how much there is then, so I can't actually put anything. So I'm going to use 600 as my initial amount because that's the earliest amount that I absolutely do know because I was told it. I know that after 8.2 hundred million years, you can barely see that 8.2, but trust me, that is 2, right? 8.2. I know that after 8.2 hundred million years, I would get 268 grams. And my goal is to figure out 13.5 hundred million years ago, how much was there? Okay, so slightly different in that we're not trying to solve for a time. I'm just trying to find how much was there this long ago. Okay. So set up my equation. A of t equals 600 e to the, not 8.2, sorry. I don't know what k is. So another problem where it doesn't specifically tell me I need to find k, but I'm just looking at the problem and knowing that if I want to figure out how much there was that long ago, I'm going to need to know k. I need k in order for my equation to work. So I'll take it, and I know if I plug in 8.2, I will get 268 grams. So I'll set that whole equation equal to 268. And we'll solve. divide both sides by 600, natural log to get rid of the e, and then divide by 8.2. Natural log alpha y equals 268 600 8.2. Negative 0.98982. So this is similar to the last one. So the 8 would bump the 2 up to a 3, but doesn't matter because since we're just looking at the third, rounding to the third decimal place, then I'm just looking at the 2, which is not enough to round it up. So, oops, why did I write that? 0.098. It makes sense that my rate is negative because it's decaying. We're talking about a problem with decay. Right. Again, I really, really hope that you're, at least on some of these, or hopefully all of these, you're doing this as well on your calculators just to make sure you're comfortable with typing these things in, because that's one of the biggest issues is people messing up how you type it into a calculator and then can't get the correct answers. So that's my hope. I have faith in you all, sort of. Okay, now that I know K, I now have a complete formula. So 600 e to the power of negative 0.098 times t. And this is going to be a little bit different because when I look at what my actual question's asking me, how much was there 13.5 million years ago? Right, so this is a difference. If I wanted to know how much is there 13.5 million years from now, right, into the future, then yeah, I would just plug in 13.5. But if it's asking me about, the other direction on the timeline, no, 13.5 million years ago in the past, we have to make a slight change. So that change is we're just going to make that negative. So negative 13.5. Okay, so when we're dealing with these problems, we can use a positive and negative value for time to represent going into the future or into the past. Right? If we want to know previously how much was there, then we'll use a negative value for time to represent going backwards. Okay, so I'll plug in negative 13.5. And this is just a calculation that I can just solve. Right? I can just plug, there's no variables in this whole part. There's no variables, it's all just numbers. So I'm just going to type in that entire thing into my calculator. 600 e to the power of negative 0.098 times negative 13.5. People usually ask me, or someone usually does, hey, if I know that both of these are negative so that they'll cancel, do I need to type that into my calculator? No, you don't need to type the negatives in. I'm just doing it just because. But if you, again, it only works if you recognize, hey, there's two negatives here being multiplied, so it should just be positive. So I'll show you that as well. So 600 e to the power of 0.098 times 13.5. So if I did not type in those negatives, I still get the same value. So no, you don't have to type them in, but just be careful that you know when you should do that, on when those negatives cancel. So nope, don't run a right with the highlighter. 2252.801 grams of uranium 235 when 13.5 hundred million years ago. MYA, classic. And that's our last one, right? I didn't mess up. Yeah. So I sent you part of the homework assignment yesterday. Those last couple problems, you might have been able to do, but we didn't talk about it because they were kind of more the multi-step problems like we did today, a couple of those last ones. So you could do those. I also sent you another assignment today that has like 4 questions on it, I think. Maybe 5. 4, maybe 5 of these that are, it takes a little bit more work. Okay, a lot of times you'll have to first solve for K, right? Even though the question doesn't tell you explicitly solve for K, but we need it in order to do the rest of the stuff that we want to do. So definitely be looking at and doing those assignments to make sure that you feel good about it and are great with the practice. Because we still have some more problems that are similar to these, like a similar equation that we're going to do. So, but it's basically the same ideas and the same setups. So you're going to need to be able to do these ones, because if you can't do these ones, then you probably definitely won't be able to do the next ones that we do. I'm sponsored by Chapstick. Use your promo code to order all the chapstick online for 9,000,000% off. Got about 5-6 minutes here right now. Any questions for me? Anyone have any good quarantine stories as well? Interesting, funny things that have happened? People that you tackled so that you could take their cans of beans or whatever it was that, you know? Your grandparents broke quarantine. Why? To go where? Did you tackle them? To come see us. Ugh. That's tough. I mean, I get it, you know. Well, by tackling your grandma, you could be saving her life, so who knows? No, please don't tackle your grandmothers. Did you tell them that they shouldn't come see you? That's dangerous, man. I mean, I know it sucks, you know, not being able to see people and being isolated, but it would also suck getting the virus. Tackling people is not within social distancing. That's true. That is true. Maybe just throw something at them, you know? Strongly worded text. All right, well, yeah, we'll see if that works. Just lock your doors. Just don't let them in. Just wave to them through the window. Hi, Grandma. Thanks for stopping by. See you next year. Okay. Well, I'm going to go ahead and sign off for a bit then. Try that homework. Let me know if you have any questions. Email me, come to office hours, etc. Hope you guys are doing well. Again, keep soldiering on. Let me know if you need anything. And I will talk to you guys tomorrow.